Now let's consider a second order reaction in a single reactant. So this would be like 2A going to product B, and the rate would be equal to K times the concentration of a single reactant raised to the second power. So it would be second over order all, and there's only a single reactant in the rate expression. Now I can write the rate as equal to the negative concentration change of the reactant A with respect to time, but I need to divide it by 2 because of the stoichiometric coefficient 2 in front of A. And this is equal to also K times the concentration of A squared. So now I have this differential equation that I will rewrite. And I will let 2 times K be equal to K prime. So now I can isolate variables. So I'll get all the A's on the left, and I'll get the T's on the right side of the equation, and now I can integrate both sides of this equation. And I'll again integrate from time 0 to time t, and at time 0 I have an initial concentration of A, and at time t I have some unknown concentration of A. I can perform the integration. So the integral on the left will give me negative 1 over the concentration of A, and I'll evaluate that at the limits from initial concentration of A to the concentration of A at time t. This is equal to minus K prime times t evaluated at the limits from 0 to t. Now K prime is a constant, so I can take it out of the integral. Now inserting my integration limits will give me negative 1 over the concentration of A plus 1 over the initial concentration of A is equal to minus K prime t. So I'll multiply through by negative 1 and isolate 1 over the concentration of A, and that's equal to 1 over the initial concentration of A plus K prime t. So this is the integrated rate expression for a second order reaction in a single reactant. So knowing the initial concentration of A and knowing the time and the rate constant, I can find the concentration of A at any time t. So this is what you should be able to use and manipulate algebraically.